everyone. Sorry, I was a little busy last week, so I couldn't actually record a video, but hey, at least I'm back this week. So today I wanted to talk about something that sort of doesn't get mentioned that much, which is that many problems, have multiple ways to go about solving them. Like, you look at the problem, and then there's one obvious way to do it, and then you do it and you come to the correct answer. But if you think a little harder, you find another solution that may well be faster. This problem over here is a great example of that. Find the minimum value of x squared plus y squared when 3x plus 4y is equal to 12. Now, let's do a little bit of thinking over here. What's the first thing that comes into your mind when thinking about how to solve this problem? For me, and I think for most people, the most obvious thing that comes into our minds is that first you write x in terms of y, or y in terms of x, it doesn't really matter. You plug that into this thing over here. Of course you'll come up with a quadratic, and then you try and find the vertex of the quadratic, which will also be the minimum value, and then you'll be done. Or to be a little more detailed, you're going to have to complete the square once you're done plugging this in. I mean, that's not too bad. Why don't we try that? See what we get. Our first step is to write like I said before, it doesn't really matter if we write y in terms of x or x in terms of y. But we're just going to go with y in terms of x, because why not? If 3x plus 4y is equal to 12, then 4y is equal to 12 minus 3x. And y is going to be equal to 3 minus 3/4 x. Or if you wanted to write that just a little differently, y is equal to 3 times the whole of 1 minus 1/4 x. Great, that wasn't too hard. Y is equal to 3 times the whole of 1 minus 1/4 x. Step 2 is to plug that into the square root of x squared plus y squared, which, if you recall, is the thing we're trying to find the minimum value of. Okay, to do that, we say x squared plus 3 squared 1 minus 1/4 x squared. That's what x squared plus y squared becomes. After that, we can do just a little bit of simplifying and expanding and stuff to get x squared plus 9 times 1 minus 1/2 x plus 1/16 x squared. Okay, we're done with that step as well. Now we come to the long step, which is actually completing the square from this. Just remember that one, okay? Okay, as I said in one of my earlier videos when I was explaining completing the square, the objective of completing the square is to come up with a perfect square trinomial so that you can find the vertex of a parabola or even the solutions. There are a lot of things you can do with completing the square. Excellent. Now, we may want to divide everything by 1/16, just to make things a little bit easier for us. So then, of course, we're going to have to move the 1/16 over here, because we can't just get rid of it, can we? Because this is an expression, not an equation. Then I'm going to skip a couple of steps here. We're going to end up with this wonderful looking quadratic, which we have to complete the square for. I don't think I said this in my completing the square video, but maybe you already know this. Completing the square gets very, very tedious if you have large numbers, especially large odd ones. But we said we were going to do this, so we can't just give up now, can we? So we're going to have 25 times x squared minus 72/25 x plus 144. So then we're going to add and subtract 36 squared over 25 squared. Why? So that we can complete the stuff inside of the parentheses. I am going to elect to be lazy and not actually solve out any of this, because number one, we don't need to. And number two, even if we did need to, we can always do it later. I'm just going to crawl back up here so that we're not stuck in the margins. Okay, now this is the simplest part. We just need to find out what this is, because it's apparent that the minimum value of this whole big polynomial is going to happen when x is equal to 36/25, which will make all of this 0. So then we only have that left over. So we just need to find the value of this. It's not too hard, actually. It looks a lot harder than it is. This looks like we're going to have to do quite a bit of arithmetic until you realize that 144 times 25 is equal to 12 squared times 5 squared is equal to 60 squared. So this whole thing over here is just equal to 60 squared minus 36 squared all over 5 squared. It's going to make sense later why I express the 25 as 5 squared. Now what's 60 squared minus 36 squared? We can quickly realize that seeing as these seem to be in a ratio of 6 to 10, well, the missing part would be 8. Because remember those Pythagorean triples? Turns out they turn out to be helpful here. So this thing is going to be 48 squared to match that ratio. And really I should switch the marker because this one's not working. Much better. So now we say this whole thing is equal to 48 squared over 5 squared. But we're not done yet because we actually have to take 1/4 of the square root of this. We just found the minimum value of this stuff. We didn't find the minimum value of this whole thing over here, did we? So 1/4 of the square root of that is going to be equal to 12/5, which is our solution. That was a lot of steps. We had a lot of calculation to do, a lot of computation. And the more steps you have, the more likely it is that you're going to mess up one step in the middle, come up with a completely wrong answer, and worst case scenario, you never catch it, and then that's that. Best case scenario, you end up catching it, and then you have to redo the whole problem. That's not what we want. So it makes a lot of sense once you even see this thing over here to think, ugh, that sounds like a lot of effort. Is this really the best way we can do it? Because there actually is another way to do it. It involves thinking of this whole entire problem completely differently. When you solve that equation, 3x plus 4y is equal to 12, Did you think, what would happen if I graphed this? Well, if you didn't think about it, let's do a very rough and very wiggly graph of this thing. I'm going to label my axes because you should always do that. Ta-da! Graphed. Yes, I know, not the best graph in the world, but it'll do. And then once you looked at the square root of x squared plus y squared, did you try and think of how that would work in relation to this wonderful graph we just drew over here? Well, you may notice that x squared, the square root of x squared plus y squared, is the distance from any point to the origin. Oh, now the problem makes a lot more sense now, doesn't it? The problem is telling us, for any point on this line over here, what is the minimum value one can achieve? What is the minimum distance to the origin one can achieve when the point's on this line? In other words, what's the minimum distance from this line to the origin? We want to figure out this, where this is like the minimum distance and stuff. Thankfully, there's a really, really helpful formula that will tell us just the answer to this. Not gonna lie, the reason why this formula is sorta uncommon is because you actually don't get to use it that much, but it's totally worth it when you can use it. It says that for any point x, y, and any line ax plus by plus c equals 0. The minimum distance between these two is going to be the absolute value of ax plus by plus c, all over the square root of x squared plus y, all over the square root of, not x squared plus y squared, how silly is that? The square root of a squared plus b squared. Isn't that nice? So now we can just quickly apply that to the origin and this line we have down over here. Then the distance is going to be the absolute value of 12 over 5, because that's the square root of 3 squared plus 4 squared. It's equal to 12 over 5. If you knew the formula and you thought of that, how long would that take you? Maybe 2 minutes? 3? That's nothing. Nothing compared to all that work we did with completing the square. And even better, it has less steps, so it's less likely you're going to mess up some computation in the middle. I hope this problem taught you that sometimes the most obvious solution isn't the best one, and that it always pays to think a little harder before jumping right in. Thank you, and see you next week. Bye!